idea of a differential equation that looks closely like the linear differential equation. This is the general form of that equation. The y dx plus p of x y is equal to q of x y to power n. So what's the difference between this and the general linear equation that we talked about earlier? Just notice when you compare the two, this is the y dx, p of x, this is y, this is q of x. The only difference is this y to power n, which is here. So this is actually what makes it non-linear, because here you have y to some power, which is not going to be 1. Okay, so when you have this kind of problem, what do? So the simple thing we are going to do is to use a substitution. So we're going to use a substitution. V equal to y raised to power 1 minus n. Of course, this will be some v which depends on x. That this is a function of x, just as this is a function of x. So why is this necessary? It will help us reduce this Bernoulli equation, which is non-linear. It will help us reduce it to a linear equation. So that is why we'll make use of this substitution. So we're going to see in an example now how this works. But generally, of course, you know you can differentiate this now. If you want to differentiate this with respect to x, we're going to have the v dx is equal to, differentiating this with respect to y, that will be 1 minus n. Okay, that's, you are differentiating y itself. Okay, then we're going to have y raised to power 1 minus n minus 1. Hope you understand that. When you are differentiating, for instance, you want to differentiate y raised to power 3 with respect to y, that will be 3y raised to power 2. What have you done? You have brought down the power 3. That's, we brought down the power here. The power here is 1 minus n. Then you subtract 1 from the power to do this. So the power has become the coefficient, and the power minus 1 is the new power. So here the power minus 1 is 1 minus n minus 1. Then we differentiate by the y itself. That's how we differentiate the y itself. That's the y dx. So of course this is always going to be equal to 1, we cancel 1, so you're going to have minus n. So at the end of the day, you're going to have 1 minus n over y to power n, then the y dx. So that will be our v dx. So from here we can make the y dx the subject. Why are we doing this? So that we can substitute. We don't want to use this substitution. That means wherever we have y, we want to replace it with something which is in terms of v. Okay, so at the end of the day, we're going to have something like this. For the y dx, instead of the y dx, we're going to have the y dx. When you make it the subject, is equal to, we are cross multiplying this now, that is going to be y raised to power n divided by 1 minus n multiplied by the v dx. So when you, so this is going to be y to power n, not y sub n. Okay, I mean, just by making the y dx the subject from here, you're going to get this, and then you can now substitute that into the original equation. Then we're going to have y raised to power n into 1 minus n, okay, multiplied by the v dx, okay, plus p of x, okay, multiplied by y. Then we're going to have this to be equal to q of x multiplied by y to power n. So that one is still there. Then now we can divide all through by y to power n. If we divide all through by y to power n, that will cancel this and cancel this. Then y to power n will come here. So at the end of the day, we're going to have y. So we're going to have 1 over 1 minus n. Then the v dx, okay, I hope you can see that on the screen, then plus p of x multiplied by y, then divided by y to power n, which is equal to q of x, because this y to power n will be gone. And then we can at this point again multiply through by 1 minus n, so that we clear up this fraction. So that's going to give us the v dx, okay, plus 1 minus n into p of x. Then what we have here will be y raised to power 1 minus n is equal to 1 minus n multiplied by q of x. So at the end of the day, don't forget this y raised to power 1 minus n is exactly what we have set v to be. So this is v, which is y raised to power 1 minus n. So at the end of the day, the substitution is now very clear. The v dx plus 1 minus n p of x then multiplied by v is equal to 1 minus n q of x. So you know that n is just some natural number, so this is no longer depending on y. So the only thing you now have left here, this is our new equation, after we have made that substitution, is now these variables v and x. So y is no longer present now. You know that n is just a number, so this is just, everything here is just a function that depends only on x, because this is going to be a number. This here also is just a function that depends only on x. So that means at the end of the day, we have reduced this non-linear equation into a linear equation. What do we mean by that? So if you compare the form of the linear equation now, you can see that you have a derivative, the v dx, which is this, and then you have this, which is some function that depends only on x, which is exactly what we have here. N is a number, n is not a variable, n is just going to be a number that you will see from the equation you are given. You will know that from the equation you are given, from the power of the y on this side. Okay, so that's the power of y that you have on this side. All right, so this is going to be q of x. This is also another function that depends only on x. So now we would have a differential equation which is linear. So we will have made this non-linear equation become a linear equation, and then we are good to go. So from that, we will get our v. When we solve that resulting linear equation, we will get our v, and then when we get our v, we'll put it back here to get our y. So life can be as easy as that with Bernoulli equation. So let's give that a try to see how it works. So we solve one of them together, then you solve the other on your own. So look at this, number 3 question. It says you should solve for or find y of x if the y dx plus y over x is equal to x cubed y to power 4. You can see because of this y to power 4, this is a non-linear equation, and it is Bernoulli equation because of its form. So let's quickly do that now. So let's write out the question first. We have the y dx, okay, we have the y dx plus y over x is equal to x cubed y to power 4. Okay, so how does this work? How does it work? So we're going to firstly notice that this is a form which is the same as our form of the Bernoulli equation. So you just first identify that this is a Bernoulli equation. It is non-linear, but it is the Bernoulli equation. So because it is a Bernoulli equation, we can reduce it by using this substitution. But firstly, identify the different parameters here. In this case, our p of x is that coefficient of y. So this is y. Its coefficient is 1 over x. That means p of x for this our specific problem is 1 over x. And then again, our q of x in this case is that coefficient of y raised to power n. That means n in this case is 4. N in this case is 4. So our q of x is x to power 3. And in this case, our n is equal to 4. So to solve this problem, we're going to use the substitution v. Of course, this is some function of x is equal to y raised to power 1 minus n. Our n in this case is 4. So this is going to give us 1 minus 4. Just give me a second. Let me change over. So that's going to give us 1 minus 4, and then that is just y to power minus 3. So we're good to go. So if you like, you can substitute that here directly, but it's not advisable to memorize this formula, so let's just work with this directly. So from here we're going to have the v, the x is equal to derivative of this. Don't forget this is a function of x itself, so we'll first differentiate this to give us minus 3 y to power minus 3 minus 1, so that's going to be minus 4. Okay, so then we're going to have this to be multiplying the y, the x. So that is that about that. You first differentiate this, then multiply by its derivative because it's a function of x itself. All right, so that's this function of a function. Okay, so at the end of the day we can get a substitution for the y dx. That means our dy dx, when we make it the subject here, is going to be equal to, you know, dividing this is going to be minus y raised to power 4. You know, this will be in the denominator, but now it's going to be y raised to power minus 4 in the denominator here, so we can bring it to the numerator as y raised to power 4, then divided by 3, then multiply by the v dx. So that's our substitution that we're going to use in this case. So, and when we do that, we're going to get, let me put on something here. So when we do that substitution, in this case we're going to get, so yeah, we're going to get this is going to be, so instead of the y dx, I'm going to put in this is minus y to power 4 over 3 the v the x, then plus y over x, then it's equal to x cube y to power 4. So I can divide through by y raised to power 4, then multiply through by minus 3 just to clear off this 3. So that is going to give me, at the end of the day, the v the x is equal to, that's basically dividing by minus y to power 4 over 3, or dividing by y raised to power 4 and multiplying by minus 3. That's going to be, sorry, so that's going to be minus 3y, okay, over x y to power 4. So I hope you got that. And then is equal to minus, because we're multiplying through by minus 3, minus 3x raised to power 3 y to power 4, then divided by y to power 4. So this, we cancel this out, and at the end of the day we're going to have this to be the y the x, sorry, v the x minus 3 over x, and that's 3 over x, then we have y over y raised to power 4, that is y raised to power minus 3, is equal to minus 3x cubed. So if you have done the substitution properly, you always end up with a function here, just like I pointed out earlier. You always end up with a function here that depends only on x, so this will depend only on x, and you always end up with a function here that depends only on x, and then it's multiplied by v. So of course you know that v is y raised to power minus 3, so you should get y raised to power minus 3 here at the end of the day. So this is going to be the v the x minus 3 over x multiplied by v is equal to minus 3x cubed. So it's now evident that we have gone from the non-linear equation we are given to a linear equation now in terms of v, which we can solve for v using the method we just used. We used for the linear equation earlier, where we got the integrating factor to be e raised to power integral of p of x, okay, dx. So we're going to do exactly that here now. So to solve this problem, our new p of x, so this is a linear equation now, so let's solve this linear equation. When we've solved it, we will now from the solution obtain our y by coming back here, okay, to obtain y. So it's obvious from here that you're going to have y to be equal to what's now v raised to power minus 1 over 3. Okay, so when you do that from here, you're going to have that. So whatever v we get from here, we'll come back to put it here to get our y, because y is actually the solution to the differential equation we were given. All right, so let's quickly do solve that this linear equation at this end. So this is going to be, of course, let's write it out first. The v dx is equal to have the v dx to be equal to sorry, changing over. So the v dx minus, sorry, why am I always writing equal to like this? It's like I need gain. So this is the v dx minus 3 over xv is equal to minus 3x cubed. So as before, we're going to get our integrating factor, which I said is denoted as mu of x in this case, and it's going to be equal to e raised to power integral of p of x dx. So in this case, p of x refers to the coefficients of v here. You know that the general form of our linear equation is the y dx. I can write it as the v dx in this case, because for this situation, v is our dependent variable, so it should be something like the v dx plus p of x v is equal to q of x. That's what we're dealing with now. So that coefficient of v is minus 3 over x. So this is just going to give me integral of minus 3 over x dx, of course, which is going to be equal to e raised to power minus 3 integral of 1 over x dx, which is equal to e raised to power minus 3 ln x. Of course, we forget the constant of integration, as I've said severally. This is going to now be what? E raised to power ln x raised to power minus 3. Then this, we cancel this. We are going to have this to be x raised to power minus 3, which is 1 over x raised to power 3. So that will be used to multiply this, and then this will become exact, and then we will solve it. So put this here now. When we put that here, we're going to have this to be 1 over x raised to power 3 multiplied by the v dx minus 3 over x, okay, multiplying, so in this case we're multiplying this by 1 over x to power 3, okay, multiplied by v is equal to 1 over x to power 3 multiplying minus 3x to power 3. So now we're good to go. So as before, we will just carefully make our analysis here. So as always, this will also be equal to d dx. So if you like, you can break this down into the v and the x and solve as we were familiar with under when we talked about inexact differential equations made to be an exact differential equation. But it's quite easy here for this case of linear equations to just proceed this way. So we're going to have this to be the derivative of 1 over x raised to power 3, which is our integrating factor really, multiplied by v. So you see that that is what you have here, actually, this entire thing here. Okay, so if you want to check that, you know, if you want to differentiate this is products of two functions, so you can differentiate this, keep this as constant. So if you differentiate this x raised to power minus 3, that will be derivative of x raised to power minus 3 with respect to x, it will be equal to minus 3 x raised to power minus 4, okay, which is exactly what you have here. That's minus 3 over x raised to power 4. So that's exactly what you have here. Then multiply by v, and then if you want to get the other one, you differentiate v while keeping this constant. That's 1 over x raised to power 3, then the v dx. So it will always be amenable to this form whenever you are dealing with these linear equations. So that's what makes it special. So even though we are using even though we are using the integrating factor, we are not going the way of that exact differential equation we have done before, because this special case, because of this special form, it's quite easier to deal with. All right, so this is now equal to, of course, this we cancel this, so this is going to be minus 3, and then we can now integrate. I can say d 1 over x raised to power 3, the multiplied by v is equal to minus 3 dx. So this is quite easy. Integrate this and integrate this. So as before, this is going to be So derivative of this, I said the integral of the anything is just anything, so this is just going to be 1 over x raised to power 3v is equal to minus 3x, of course, minus 3x. Integral of the anything is anything, so anything here is x, so this is going to be minus 3 multiplied by anything, that's minus 3x. So then plus that constant of integration. So from here also we can clear the coefficient of v, so this will be v equal to, when I multiply through by x squared, x cubed, that's going to give me minus 3x to power 4, then plus cx to power 3. So life can be as easy as that. So that's going to be our v. So don't forget that to finalize our solution, it is y that we need, and we have said that v is equal to y raised to power minus 3. So that means that y raised to power minus 3 is equal to cx cubed minus 3x to power 4. So from here we can get y to be equal to cx cubed minus 3. You can see that cx cubed minus 3x to power 4 raised to power minus 1 over 3, and that will be our solution to the Bernoulli equation we were given. So that is that about that. It's that easy to deal with. And then for the next one, we talk about what we call the Riccati's equation. So you can give this one a try. So in this case, your n is 2, so it's of the same form as this. This is the y dx, y dx, y over x. So p of x is y over x, q of x is x minus 2 here. Then you make the substitution as before. V is equal to 1 minus n. So this is going to be v is equal to v is equal to y raised to power 1 minus n. So this is going to be, the substitution you use here will be v equal to y raised to power 1 minus 2. Then go ahead and give that a try. So you should get your answer using this approach as before. So now we now consider Riccati's equation. That is the next kind of non-linear differential equation, okay, that we'll consider to make it. We're looking at how to make it linear and possibly solve this again. So you may not bother about this part anyways, but I just have to teach you because it's on your material already. But usually they at least said any question on it, because it's I don't know, I've only ever seen this particular question on Riccati's equation. It has always been in the lecture materials, but then it's okay. Look at the general form of Riccati's ODE. So let me show you that. Let me write that for you from the material given. This is Riccati's equation, or Riccati's ODE. Riccati ODE. So if you are already tired at this point, you may not bother about this part actually, but let's just do it for 3 records. So this is going to be, and then we don't know, they might just shock us, so just good to know it. Riccati's ODE is actually going to be generally in the form the y dx plus p of x y is equal to q of x y squared plus h of x. So look at it now. So this is quite similar to the Bernoulli's equation with, so of course if this h of x was not present, it would be like the Bernoulli's equation. Remember the general form of the Bernoulli equation. So we add this as the general form of the Bernoulli equation. So this would have been just same form as the Bernoulli equation. Okay, you cannot see it. Same form. It would have been just the same form as that of the Bernoulli equation. So it would just be a Bernoulli equation with n equal to 2. I mean, that's the 2 we have it. But then we now have another function written with it, h of x, which does not carry y or any derivative of y. So that's what makes it the Riccati's ODE. So this h of x in particular. So when we have a situation like this is a special kind of differential equation. For you to solve this differential equation, now this differential equation will usually have what do you call it now? We usually have two solutions, okay, at least two solutions, and then you will be given one of the solutions, okay. So when you're given one of the solutions, then you'll be asked to find the other solution. So that's always the approach to this kind of differential equation. So you cannot find you are not always required to find the two solutions yourself. You'll be given one of the solutions from which you will get the other solution. So that's exactly the problem we have here. So the problem says that given that the equation this is obviously a recursive equation, is equal to all of this. It said it has a solution y equals to x. So we're going to rearrange this so that you see it's a recursive equation. Then you said find the other solution. So you are given one of the solutions, then you ask to find the other solution. And so to do that, we will always make use of this substitution. So let's say you are given one of the solutions to be v of x. Then for you to get the other solution, we will usually use the substitution w is equal to y minus v. Okay, so we use that substitution to get our second solution. That means we will substitute this into this differential equation, so to help us reduce the differential equation to another form we are already familiar with. Okay, so let's give this a try now. In this example we try. So we are told that the y, the x is equal to the y dx is equal to x to the power 3 into y minus x all squared plus y over x is equal to x to minus 2, sorry, x to the power minus 2, then y to the power 2. So what am I writing now? No. Sorry, please. This is you can see that I'm tired too. But then what has to be done has to be done. This is the y dx is equal to x to the power 3 into y minus x all squared plus y over x. So we can write this, we can just open up the bracket to see that it's actually of the same form as this recursive equation, general recursive ODE. So this is going to be the y dx equal to x to the power 3. This part is not necessary, but it's good that we just do it. Into this is going to be y squared minus 2xy plus x squared. So I believe everyone knows how we came about that. Let me just expand this. Then plus y over x. So at the end of the day, you're going to have something like this. This is going to be x cubed y squared minus 2x to the power 4 y plus x to the power 5 plus y over x. Okay, and then we can move all the terms together just to have a form similar to our general form. So this is going to be plus p of xy. So you can see what we have on this side is p of xy. That means those terms that contain y, we're going to move them. So that's, I know those terms that contain y square is separate. So the terms that contain y here are this and this. So we'll move them to this side. That will become plus 2x to the power 4, then minus, so this will become minus when it comes to the minus 1 over x, okay, multiplied by y is equal to then q of x y squared. The ones that carry y squared, that is x cubed y squared. Alright, so that's x cubed y squared. We always have that, and then some other function that depends only on x, that is this one here, plus x to the power 5. So this is actually obviously a recursive ODE. So if we are to compare with this general form, for instance, if we are to compare with this general form, it is evident that